So I want to start by just showing you something that I tried to show yesterday, but I think I kind of failed. So I want to start from here. I want to figure out the result of taking the integral of the area of a disk. I figure if I add up all the pieces of area of a disk, I should get the area of a disk, right? What's that? That seems pretty true. So, like yesterday, what I'd like to do is identify and describe a single piece of area of this disk. I'm going to do so by just drawing a small box to represent a single piece of area of the disk, dA, piece of area. Okay? Any question about what dA represents? Now, it's a square-ish. My thoughts are, if I have rectangular information, I can find the area by the product of the length and the width. Right? That's how we would generally find the area of a rectangular portion. So I think my dA could be the product of a length and a width. But also, I would like to be able to do a sum. And generally a sum requires some part that I can increment a little at a time. Right? We've done a summation before where we increment things, right? Do you remember adding up the 5 pieces for the meter stick? We incremented where each center of mass was? Well, I want to increment where every single piece of area is. So I want to start out by trying to find a way to point to each area, something that I could use for every single area that there is. So I'm going to establish a point of reference, the center of the circle. I'm going to make all of my squares measured relative to the center of the circle. So I'm going to start at the center of the circle and identify one corner of the square. And I'm going to label this R because it is radial. Now, to identify that corner, I don't just want R because that's a lot of different squares, right? There's probably an R over here too, right? That would be a totally different square. So at the same time, I'm going to try and order which square I'm looking at by establishing a starting point on my circle and using another variable to tell me where I am along the circle. Now, if I use R and theta, can I point to every single possible square on this disk? I believe so. Let's assume I could start with the angle being 0. I could go from 0 to capital R, and that would give me every single square along that particular radius, right? Then I'd go over and do the next one, go over and do the next one, and eventually I'd add up all the squares. All right. Now my squares are really, really small. The idea is that you're using calculus for this, so when I say square, I'm talking about something that is super, super tiny. I've drawn it big so that we have some way of looking at it, but it's actually very small. But I would like to, at this point, kind of zoom in on this piece and deal with the idea that I would like to express L and W in terms of my pointer variables, because we want to be able to add them together. So I want to use something that I can increment the same way I increment any summation. So I think this will be relatively easy for one of them. I think we can all agree that if I go out a distance R, this is just a little bit more in the direction of R. So I will call this a little more in the direction of R. Good so far? Got those compasses ready? Because I want to describe this portion right here. And I think the best way to do it is to go out a distance R and then move it a little bit in the direction of theta. Do you understand that's what a compass does if you wanted to draw just a small piece of arc? You would open it up to a distance, r. You'd put the point at the center, you'd put the drawing portion at the square, the corner of the square you're trying to describe, and you would go a small distance in the direction of theta. Would that not create a small piece of arc? Do you see how your compass works, right? It doesn't have to draw an entire circle. It can draw a small piece of arc length. This arc length would be r d theta in length. Just like a compass drawing a small piece of arc. Do you see what that is? D theta is just the small motion of the compass, creating a small little segment of length. Do we all follow so far? Now, I will point out that for this to truly be the area, we would expect this side and this side to be the same length, and this side to be the same length. And although I think the DRs work, I think these two are the same length, I think there's a reasonable argument to be made that this might not be the same length as this. That's a reasonable argument. I will throw it all away and say, magic of calculus. Since DR is really, really small, we can state that those two are nearly the same length. And if you don't believe me, I'm going to try and prove it. Okay? So, seems to me that if we're careful now, our dA is going to be length times width. dr times r d theta. Length times width. All good? Everybody follow along with my arguments? So, I want to move one step further. I want to prove that if I add this up for every single piece of area, I will get pi r squared. So, I'm going to replace dA with dr times r d theta. Now, the first thing you should notice is that I have two derivative variables. That means two summations. Because we know that r is going to go from 0 to r. And theta is going to go from 0 to 2 pi. So I will need to integrate twice. An r for every theta. Everybody okay so far? Now, if you're not doing this in calculus yet, don't fret. It's generally calculus 3. And I don't care if you don't know about it. You just need to know a little bit. And it'll be enough for us to do this activity. First things first, though, when I'm saying that we're setting our limits, I want to set reasonable limits. Every single angle has to start at 0 and go out to r. Right, then we move over an angle and do it again. So you see how this is a sum within a sum. We will do this for one theta, then go over and do it for another theta. We'll sum both of them. Follow me so far? Luckily for us, every single theta goes from 0 to r. And for every single r, there is a place on the disk that is from 0 to 2 pi. You follow what I just said? If I pick a theta, say this way, there will be an r along this entire length from 0 to r. Also, if I pick a specific r here, there will be a piece of mass related to everything within the same circle from 0 to 2 pi. Now, that's not true for every shape. It's true for a disk. I mean, there are shapes where that's certainly not true. like a pinwheel, would there be 0 to r for every theta here? No. So I would probably need to know how theta and r are related, so that when I change from one theta to another, I have a new range of r. But we're not going to do that. We have a disk. And like I explained, for every single r, I have 0 to 2 pi, and for every single theta, I have 0 to capital R. Because of that, I can split this into two integrals. One for dr and one for d theta. All I have to do is collect terms first, meaning anything that has r in it needs to go with the integral for r, and everything with theta in it needs to go with the integral for d theta. I only have one r, so I'll put the r there. And it goes from 0 to r, and this one goes from 0 to 2 pi. Now again, if that weren't true, the order in which I did the integral would matter, and I would have to have a relationship for r and theta to work that out. And trust me, that pinwheel I just drew, although messy, there is an equation, a polar equation for that particular pinwheel. And if you wanted to integrate it to find the area of that pinwheel, you most certainly could. But you would have to know the polar equation that relates r and theta. So polar equations are a thing. I'm sure you've learned about them already. Actually, I'm not sure about that. At this point in my career, I have no idea what you've learned. You have proven me to the contrary a couple of times already. So raise your hand if you've dealt with polar plotting and polar equations. So you know about some. Good. So you know that there are relationships that could be placed in here that relate r and theta for a polar plot. Good. We don't need that though. It's a disk, right? It's a disk. So here we go. We just have to integrate. So that's pretty straightforward, isn't it? When I integrate r, I get r squared over 2. Evaluated from 0 to r. And d theta has no variable, so that's 1, or theta to the 0 power, or theta, evaluated from 0 to 2 pi. All good? Any questions about those choices? Put in my top boundary, subtract my bottom boundary, and get r squared over 2 minus 0 times 2 pi minus 0. And pi r squared, right? 2's cancel. I mean, we're not surprised by this, are we? We expected to get pi r squared, or we got pi r squared, so that's nice. Everybody follow the argument okay? Because we're about to change the argument. I want to use this argument to do something else. So do we follow along with what I did? I want to prove to you that first, our little piece of mass really can be described as having an area of r times r d theta, dr times r d theta. And that with the magic of calculus, dr being infinitely small, it can be treated like a small rectangle. And if we add up all of those rectangles, we do get the area of a circle. Does that make sense? Did you follow along a little bit? Because we're going to have to do a disk for the moment of inertia. But I wanted to make sure that you followed along and saw that we did indeed, using a square, prove that if you add up all the squares in a disk, you get the area of that disk. Is that okay? You don't seem convinced, but I don't care. We have to move on. I did my best to convince you. So can I move on? Yes. So now we want to find the moment of inertia of the disk. I want to use the same argument. I want to start by identifying a small square on the disk. I think I can go through this initial part pretty quickly. But let's start with a few things we know. Let's say the disk has mass m and radius r and area pi r squared. Let's also be reminded that moment of inertia is the sum of the perpendicular distance to each piece of mass over the entire mass. That's how we calculate moment of inertia. I said to you yesterday to draw your object and then identify a piece of the mass. So we are identifying a piece of the mass. This piece represents dm, a piece of the mass. Then find a way to point to that piece, putting in reference as necessary. So R points to the first corner of that piece. I'm going to choose the center as my reference for R, and I will pick a random location as my reference for theta. I'm going to say that this piece has an area dA, and that based on our argument a few minutes ago, that area can be written as dr times r d theta. Right, all the same things we did before. Starting out with representing a piece of the mass, trying to find a way to point to it, identifying that I can point to every piece of mass with the variables that I've chosen. Consider the limits of those variables as being from 0 to capital R and 0 to 2 pi, and write something out that could represent the shape of the object versus its mass. So dA represents the shape of the object versus its mass. The next thing I said you had to do is create a ratio, and that's the ratio of the mass to the shape of the object. So dm is related to the area of the object, as m is related to pi r squared of the object. This is actually a density, and for this it's a surface or areal density. There's a whole set of symbology that goes along with this, but I'm going to ignore it for today. But we should come back to it in the future. There are symbols that represent surface density, volumetric density, and linear density. Now remember the next step? Solve this for dm, because we're going to use it for substitution. So dm equals m over pi r squared dA. But again, dA, I need to replace with something that has my pointer variables in it. So dm equals m over pi r squared dr times r d theta. So now I have, I believe, something I can use for dm that's in terms of the shape of my object, that has variables that I can use to point from one portion of the object to the other portion of the object. Any questions about those choices yet? All right. One more thing to do. This r is a placeholder that represents the perpendicular distance from the axis of rotation to our piece of mass. Can we agree that the r we have in our diagram is equivalent to the r that's in this particular equation? That our radial distance is the perpendicular distance to our piece of mass. You guys following along? They are the same thing. They represent the same thing. If so, I believe I can assemble my integral. I'll start with r squared. I'll substitute in for dm m over pi r squared times dr times r d theta. I'll recognize I have two integrating variables, so I will put in my second summation to emphasize that we're summing over two sets of variables. Now, I want to reorganize this, perhaps pull out something that is common to every factor and put in my limits. So I think the mass of the disk is common to every factor. And I think pi r squared, common to every factor, right? Those are constants. They don't change with where I am on the disk. So I will pull out the m over pi r squared. I will separate and have r cubed dr. I've collected all the r's and put them with dr And I'm going to start at 0 and go to capital R. And that just leaves d theta, which I'm going to start at 0 and go to 2 pi. Just like we did for the area, but this time I have more things that deal with r, so that's why there's r cubed there, because there's already an r squared there. Any question about all those choices? Well, this part's pretty easy, right? We've done this before, so I think we can kind of do this again. This will equal m over pi r squared. Antiderivative will be 1/4 r to the 4th. Add 1 to the exponent, divide by my new exponent. So r cubed becomes r to the 4th, but I have to divide by 4. Evaluated from 0 to r times just theta, evaluated from 0 to 2 pi. That all good for you guys? So put in my top and subtract by putting in my bottom. So m over pi r squared r to the 4th over 4 times 2 pi. Well, r squared cancels with 2 of those. Pi cancels with pi. And 2 cancels with one of the 2's in that 4. You guys see all of that? Leaving me with 1/2 m r squared, the moment of inertia of a disk. All good? Did I go too fast? So now you've seen moment of inertia of a disk. Your book does it different, but since none of you have one, you don't know that. The book does it with a bunch of concentric rings. Uses mr squared and sums over all the different rings. It's an interesting thing, a nice derivation. It assumes you know the moment of inertia of a ring before you do it, but I think you can reason out that the moment of inertia of a ring must be mr squared. Because if we consider a ring, nope, that's not a ring. If we consider a ring, Mr. Shelton, just do it. What is wrong with me?
Nothing's wrong.
Something seems very wrong. But there we go. If we consider a ring for just a minute, I don't really think we have to work out the moment of inertia. We could, but do you realize that every piece of mass is a distance r away from the center? Wouldn't you agree? I mean, if you don't, if you want to work it out, this is a length. So I'll say that this is length dl, and it has mass dm. I don't really want to do this. I think you should. But if you're desperate, we can show that this has to be mr squared. But can't you just reason that if the moment of inertia is supposed to be how far away each mass is from the axis of rotation, every piece of this mass is the same distance from the axis of rotation, and that distance is the radius? And that seems like the reasoning part. You can do the calculus of it. It would be dm over r d theta, but r would be just capital R because every single piece of length is capital R away. And that would be equivalent to the mass of the ring divided by its circumference. Work this out. Sum it from 0 to 2 pi, and you'll get mr squared. I do want you to think about is consider this, but not the way you think I want to consider it. I'd like to do something that actually is interesting, at least interesting to me, and consider spinning this about a diameter. Because this might actually be somewhat interesting if we spin it about a diameter. There. So, if you don't know, if it's a line that's been bent into a circle, it has mass m and length 2 pi r. I will define a piece of it as being dl, which is a distance r away from the center. Every piece will be the same r away from the center. That good? But the size of that piece of mass, the part that is dl, I will write as r d theta, and I will define theta as the angle from the top of the axis of rotation. All good? Any questions about my defining variables and what I have here? I'm doing all the same steps as before. Have I done anything weird yet? Identified a piece of the length. Can I address every single piece of length using r and theta? Okay. But r is a constant in this case, right? It won't change. So I believe my next step is to say that dm is to dl as m is to 2 pi r. That all good? So dm will be m over 2 pi r dl, but dl is r d theta. All good? I'll cancel out the r. I now have my substitution for dm. So we can build our integral. My integral tells me that I have to take the perpendicular distance from the axis of rotation to my piece of mass and then multiply by my piece of mass, which we have now as m over 2 pi d theta. Now, I take issue with r. I think r is that. Isn't that the perpendicular distance from the axis of rotation to my piece of mass? Are we sure that we understand what I'm pointing at? I had to demonstrate it to Andrew last class period, but I knew I was helping out a lot of people. Does anybody need it demonstrated? R is going to be r sine theta. Do you see that okay? You should consider working this through, but you'll understand why it's a problem. You should pack up, but look carefully on my screen while you're packing up. This is what you'd have to do. The problem is that I don't think most of you know what the antiderivative of sine squared is. And it's not on our equation sheet, so we wouldn't be expected to know it. But I know a few of you do, because you've had calculus, so you know that this is quite a capable integral. Though, there's something that you should do tonight that would be wonderful practice. I don't have too much confidence, but let's say that you'll run right out after this is done and you'll say, wow, I have to try that. Mr. Shelton said to. And he would be disappointed with me if I didn't. I might never know. In your chart is a thick ring. A thick ring has like a inner radius and an outer radius. You don't have to do a whole lot of work for this. If you figure that there's a square of mass somewhere in the thick ring, the only difference would be in your integral for the summation. You wouldn't start at 0. You would start at the inner radius and go to the outer radius. You should try this. But be careful, this is not pi r squared. You'll have to put the actual area of a disk with a hole taken out of it, which probably is the area of an entire disk minus the area of the hole. So if I were to just throw this down, because you guys are smart and you may actually want to try something, that would be the area. Now this works out to be something kind of interesting. You might need to know the difference of squares to get it to simplify. But it works out great. You should try it. What I'd like to do